Hey everybody, sorry I couldn't be here with you today. I was feeling much worse as the day went on. Went to the doctor, got some medicine, so I'm home for today. I'm going to go ahead and remind you, even though I shouldn't have to, I'm going to do it anyway. Please be respectful to each other and to your substitute, whoever you may get. Certain things that you shouldn't have out would be like your cell phones or work from other classes. Try and stay focused on what we need to get done here today in this video, and be respectful and be quiet and follow directions, please. I hope to hear nothing but good reports when I get back. The first thing I would like to do is check your homework, so if you don't have it out already, go ahead and get it out. At this time, I would like to ask the substitute that if there are a lot of people getting their homework out, to please pause the video and then resume when we are ready to check it. Only check this homework if you've done it. Don't copy down the answers. It's not going to help you in the long run. You do have a quiz on Friday. Even though I'm gone today, you have a quiz on Friday over 7-1, 7-2, and 7-3. So starting with your homework, all four of those first triangles are similar. The first one is by side angle side similarity. The second one is by side 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 similarity. When putting corresponding parts together, all of the ratios reduce to 3/4. The third one is by side angle side similarity again, and then number 4 is yes by angle angle similarity. Even though you didn't have this 30 degrees or this 60 degrees, you could use the triangle sum theorem to figure out that if you had a 90-degree angle and a 60-degree angle, the angle M had to be 30, and over here angle T had to be 60. So all of the angles are equal to each other. Then moving on down to numbers 5 and 6. I tried to highlight the corresponding parts for you so you could see the pieces that you should put together to set up your proportion. I started with 15 over 12, EB over BC, and since I went from the left triangle to the right triangle, 15 over 12, I did x plus 5 over x plus 1 on the other side of the proportion. Solved for x, and x is 15. Plugged it back in to get AC. AC is this x plus 1 expression, so 15 plus 1. Your AC length is 16 units. The similar triangles will look something like this. Triangle EBD is similar to triangle CBA. You could have a different order than that. Just make sure the corresponding congruent parts are in the same order. And these two triangles are similar by the angle-angle similarity postulate. They each have a right angle and then another congruent angle inside. Number 6. Again, I highlighted the corresponding parts together so you can see how I set up my proportion. I put 4 over 6. I went top triangle to bottom triangle. So 4 over 6 equals x over 12. That's your proportion. Cross multiply and you get x equals 8. And then the length of JK is just expressed with x. So the length of JK is 8 units. Again, these two names could be a little bit different. Just make sure that you have congruent parts together. And the method here again was angle-angle similarity. That seems to be the one that we use most often. Okay, looking on the back. Number 7 and 8, on both of these, I drew them as two separate triangles because I think it's important that we look at them that way. For number 7, we have this smaller triangle, triangle QRS, and this slightly larger triangle QPT. Since we have parallel lines here, we know corresponding angles are congruent, angles R and P, and then angle Q is in both of the triangles. So that is our second set of congruent angles, which is why these two triangles are similar by angle-angle similarity. And then having those two separated helped me better set up the proportion. So I went with the bases first, well, second, but I put 12 over 16 for the bases. And then the sides here in the same order would be x and 20. So your proportion could look a little bit different than mine, but even if you set it up differently, you still should have come up with an answer of x equals 15. And then this part was a little bit tricky. I hope you caught it. You were looking for the length of ST. ST is over here. The length that you found, x, is 15. If this whole side is 20, then we take 15 away from that to find that the length of ST is 5 units. Looking at number 8, again, I drew it as two different triangles. We had corresponding angles again, and then a shared angle in those two triangles, so these two triangles were similar by angle-angle similarity, just like many of the other ones were. And then to set up this proportion, I put 6 over 14, the left-hand sides, and then I put x plus 2 over 4x minus 1. And you might be wondering where this 4x minus 1 came from. That is the entire length of ST, and if I look back up here in my original diagram, ST, it's both the expression 3x minus 3 and the expression x minus 2. So that's a total of 4 x's, and then negative 3 plus 2 is negative 1, and that's where that 4x minus 1 came from. When you cross multiplied, you did get a decimal, but that's okay. X is 3.4, and then finding the length of VT, VT is this expression x plus 2, so we do 3.4 plus 2 to get a length of 5.4 units. And again, you can see the similarity statements here, and that we knew these triangles were similar by angle-angle similarity. I wouldn't be surprised if we had some questions on number 9. I drew 2 pictures. I drew one with a statue and one with May, I'm not really sure how you say her name, but we knew both shadows. The statue shadow was 10.5 feet, and May's shadow was 3 feet. May was 5 feet tall. We don't know how tall the statue is. So I compared shadow to shadow, May's to the statues, and then height to height, May's to the statues. And when I cross-multiplied there, I found out that the statue is 17.5 feet tall. And then here are your answers for numbers 10 and 11. If at any point you need this paused or you would like to substitute to go back, please just raise your hand, and I'm sure that they can back this up to get you to whatever problem you need to look at more closely. Okay, so once you have that checked, go ahead and put it away. The next thing we're going to do is our notes for today. These notes are not on the quiz, but they are in this chapter, so we're going to go ahead and move forward with these notes. Again, your quiz is over 7.1, 7.2, and 7.3. So, with this 7.4 notes, we are talking about parallel lines and how they cut different lines or shapes into proportional parts. So our objectives today are to use proportional parts within triangles and use proportional parts within parallel lines. Again, I have that vocabulary term up there for you. What is the definition of similar polygons? I'm going to leave that to you to fill out, and we can talk about it again when I get back, but we just talked about it yesterday. So, what is the definition of similar polygons? Give the most specific answer that you can give, and if you've got to look back at your notes or ask somebody else at some point, that would be fine too. But we're going to go ahead and move on. I have all my highlighters ready and all my different colored pens, so here we go. The first theorem we're looking at is called the triangle proportionality theorem. It is also referred to sometimes as the divided sides theorem, and you'll see why here in just a minute. If a line is parallel to one side of a triangle and intersects the other two sides, then it divides those two sides, or segments, into proportional lengths. So what we have happening here is we have this line EF, that is cutting through the triangle. And as it's cutting through the triangle, it is intersecting two sides. We know that segment EF is parallel to segment BC, so I'm going to go ahead and put the parallel arrows there. And if that's the case, what happens is those two sides that are being divided, hence it being called the divided sides theorem, are proportional. So AE to BE, the ratio AE to BE, so one part of this side AB and the other part of this side AB is equal or proportional to the parts on the right-hand side, AF and FC. The converse is also true. So the converse of the triangle proportionality theorem, and just like with so many converses, it really is all about, do we know we have parallel lines, or are we trying to show that we have parallel lines? And in the theorem itself, we were given that there were parallel lines. That was something that we knew. But here, it's something that we're trying to show. So the converse says, if a line intersects two sides of a triangle and separates the sides into proportional corresponding segments, then the line is parallel to the third side of the triangle. So in this case, what we're told is that we have proportional sides. So we're told that the ratio of JL to LI, the two parts of that side, is equal to the ratio of the parts JM and MK on the other side. And if that is the case, then that is enough to show or to prove that this line, JL, is parallel to this base IK. So it's the converse. It's all about, do I know that they're parallel lines? If I do, then I can say these sides are being cut proportionally. But conversely, thinking about it backwards, if I know the sides are cut proportionally, then I can make the conclusion that we have parallel lines. So let's try and do a couple of examples here. For numbers 1 and 2 on our examples, we're going to use this diagram up above and some information. So let's go ahead and label our diagram with the information. So we know that line LM is parallel to line IK. So I'm going to put arrows there. And that should kind of jump out to you because we can use the theorem, don't have to use the converse because we're told that the two lines are parallel. We also know that the length of JL is 3 inches. And we know the length of LI is 9 inches. And we know the length of JM is 5 inches. And I'm going to go back over that in pen so that hopefully it's easier for you to see. So we have a length of 9, a length of 3, and a length of 5. What we're trying to do is solve for the length of MK. I'm going to go ahead and put an X there. That's our unknown. So we're actually going to approach this in 2 different ways. One way is a way that I already showed you on when we were grading yesterday's homework, but another way is using the divided sides theorem. So the first one, number 1, says set up a proportion and solve for MK using the triangle proportionality theorem. And that theorem says that if we have parallel lines, which we were just told that we do, that the sides are being cut proportionally. So in other words, I can say JL to LI is proportional to JM to MK. So a proportion would look like 3 to 9 equals 5 to X. So by using the triangle proportionality theorem, which is also called the divided sides theorem, because I have a parallel line that's cutting 2 sides, I can actually take the parts of those 2 sides. It really truly is a shortcut to set up the proportion. So then if we cross multiply, we get 3x equals 45. And then if we divide by 3, x is 15. It asks us to find the length of MK. So if I go back up to my diagram here, MK is what I represented x with. So MK is 15 and our unit is inches. Now I'm going to show you another way to do this, a way that you would have previously known how to do it. So we can actually think of the triangle proportionality theorem as a shortcut. The next way we're going to do it, number 2, is by setting up a proportion and solving for MK using the definition of similar polygons, which is what I wanted you to consider earlier, was the definition of similar polygons. In case you didn't write it down or write it down correctly, similar polygons have 2 things that we need to know. One is that the corresponding angles are congruent, and one is that the corresponding sides are proportional. So if we go back up here to our picture, again, we really have 2 triangles here. We have a smaller triangle and a big triangle. And those 2 triangles should be similar in order for us to be able to set up a proportion. So by using the definition of similar polygons, let's draw these triangles out individually. So I'm going to start with the smaller triangle, which is triangle JLM. And triangle JLM has a side length of 5 and a side length of 3. JM is 5 and JL is 3. Now I'm going to look at the larger triangle, and that triangle is JIK. And our side lengths here, here's where we have to be careful. All the way from J to I is a side length of 12, because it's 9 and 3 put together. But all the way from J to K is a length of 5 and a length of X. In order to combine those, just like we did 9 plus 3 to get 12, we will express this as 5 plus X. Some people want to try to make that 5x, like 5 times x, but really we're adding those 2 parts together to express the total side. Okay, now deciding whether or not these 2 triangles are similar. Well, first of all, we do have these parallel lines, and these parallel lines will create corresponding angles. So I know that angle L is congruent to angle I. And then I also know that both triangles share angle J, so angle J would be congruent to itself, which means there's enough information to say that these two triangles are similar by angle-angle similarity. So now we can put corresponding parts together. That would look like, let's say I did this left side, the shorter side, and the left side over here, JI. I can put 3 to 12, staying there on the same side of the triangle, equals, we went small to big, so we'll go small to big over on the other side of the proportion as well, 5 to 5 plus x. When we cross multiply here, we are multiplying 3 times the expression of 5 plus x, and then 12 times 5, which is 60. We'll distribute to both terms. 3 times 5 is 15. 3 times x is 3x. Subtract 15 from both sides, and we get 3x equals 45. If we were to divide both sides by 3, then we get x equals 15. And again, x is what we used to represent MK. So again, we come up with the answer, MK equals 15 inches. So the thing of it is, the triangle proportionality theorem will only work sometimes. The triangle proportionality theorem is only going to work if you have parallel lines, and it's only going to work if you have two sides that are being divided. But we will come to other examples today where you do not have two sides that are being divided, and so you instead have to use the similar polygons, the similar triangles, and truly look at it as two different shapes. Let's take a look at number 3. There's going to be one situation where you can use the divided sides theorem, and one situation where we're going to have to use the definition of similar triangles. So it is given, we know that PQ is parallel to OR, segment OR. Set up a proportion and solve to find the missing values of the variables. Well, let's start with x. When I look at x is part of a side that is being divided, segment PN. I have another side that's being divided, segment NO. So since I have two sides being divided by parallel lines, I can use the triangle proportionality theorem, or what we said could also be called, and hopefully you're seeing why, the divided side theorem. We have a parallel line that is dividing two sides. So in order to find x, I can set up the proportion x to 3 equals, so since I went x to 3, I should then go 12 to 4. Cross multiply there. 3 times 4 is 4x. 3 times 12 is 36. Divide 36 by 4, and we get x equals 9. So there's one variable solved for. Now y. Not y as in why is that, but I mean the variable y. Take a look at that. We have to look at this as a completely separate problem. And the thing about this segment, OR, where y is, that is not a divided side. That is an entire side by itself that is not being cut apart by anything. And if I then find a corresponding part to go with that, that corresponding part would have to be this segment PQ that is also not being divided. So we have to look at these as two separate triangles. If I look at the smaller triangle, try to find room here to draw it. If I look at the smaller triangle, then we're looking at triangle ONR. That triangle has a side of x, which we just found, that's 9, and a side of 12. And y is OR. If we look at the larger triangle, these aren't my best drawings, but you get what I'm talking about. That's P and Q. Now be careful when we're labeling here. This is 3 and 9 for PN, so this is a side of 12. the entire length of NQ is 12 and 4, which is 16. And then this side, PQ, is 20. You have some options here, but one thing that's really important is that we have to put, when we're writing our proportion, we have to put y and 20 together in a ratio. So I'm going to start this proportion by saying, or comparing y to 20. So y to 20 equals y to 20. And you could do 9 to 12 if you want, but I'm going to use 12 to 16 because I didn't calculate any of that side. And if for some reason I had made an error when calculating this x value, then I would turn it into another error in this problem as well. So I'm going to go ahead and use the links that I already knew. So I'm going to use this side of 16, which corresponds with the side of 12 on the smaller triangle. So y to 20 equals 12 to 16. I'm going to grab my calculator for that, do our cross products here, get 16y equals 20 times 12, pretty sure that's 240, yep, equals 240, divide by 16, and we get y equals 15. So for part of this problem, we used the divided sides theorem when we had two sides that were being split apart, but then we had to use the definition of similar triangles because we were dealing with two sides that were not being split apart. Okay, let's look at a slightly different situation, and we will be using the converse here, and the reason I say that is because we're determining whether or not we have parallel lines. So if you look at this picture here, we're trying to decide or show or determine that segment DE is parallel to segment BC. So if we go back up to the converse of that theorem, what we then need to do is show that we do have proportional sides. So let's label our diagram with the information that we know. And the information that we know is that AD is 15 centimeters, and DB is 12 centimeters, AE is 10 centimeters, and EC is 8 centimeters. Now, in order for these two lines, in order for segment DE and segment BC to be parallel, then they should be cutting both of these sides proportionally. So let's compare the different parts. We would compare, let's say we do 15 to 12 first. 15 to 12. Okay? So we think, what does that reduce to, 15 over 12? Well, 3 goes into both of them. So 15 divided by 3 is 5. 12 divided by 3 is 4. So we have a simplified ratio of 5 to 4. Hopefully, when we set up a ratio of the other parts on the other side, those will also reduce to 5 to 4, so let's check. If we compared 15 to 12, we should go in the same order over here on the other side. We'll go 10 to 8. Those are both divisible by 2, so 10 divided by 2 is 5, and 8 divided by 2 is 4. So it turns out these sides are cut proportionally. So we'll say yes, segment BC is parallel to segment DE because the sides were cut proportionally. Okay, moving on, just a couple more things. We talked about midsegments in a trapezoid last chapter. There is such a thing as a midsegment of a triangle. The midsegment of a triangle is a segment joining the points of two sides, the midpoints of two sides of the triangle. So if I were to highlight things here, I would say the definition of a midpoint is a segment joining the midpoints of two sides of the triangle. And we do have a theorem that goes along with that. The triangle midsegment theorem, a midsegment of a triangle is parallel to one side of the triangle, and its length is 1/2 of that same side. So if we take a look at our diagram over here, what we know, or what I'm telling you, is that we do have 3 midpoints. So remember, if you're seeing a midpoint on a diagram, you're probably going to be seeing some tick marks that show you that D is right in the middle, and that F is right in the middle of this side over here, AC, and E is right in the middle. So we have three midpoints happening here, D, E, and F. So these segments joining them are the midsegments. So segment DE is a midsegment, and segment DF is a midsegment, and segment EF is a midsegment. If we just look at one midsegment in particular, like in this example here, it says AB, segment AB, side of the triangle, is parallel to segment EF. And EF is the midsegment that connects the midpoints that are not on the segment AB itself. So these two segments are parallel to each other. So we could put some arrows on here. And then the second relationship that we know is that those two segments that are congruent to each other, EF, the midsegment, is 1/2 the length of the side that it is parallel to. It's honestly a pretty easy concept. If we look at example number 5, J, H, and P are midpoints of their respective sides. Find the value of X. Well, X is right here on this midsegment, JH. So you should ask yourself, I know that a midsegment is parallel to one side, so which side is it parallel to? Well, definitely not parallel to side LK, it's intersecting it. Definitely not parallel to side MK, it's also intersecting it. And we are told that if you have a midsegment that it is parallel to this third side, that it's not intersecting. Not only is it parallel to that side, but it's half of that side. So really, X, what we're looking for is just half of this parallel side, 30. So X is 15. That's it. The midsegment is half. However, when we use parallel lines, we could also have some angles that show up there. We could have corresponding angles or alternate interior angles, etc. So in this case, when we're trying to find the value of X, X is an angle measure. So we kind of have to get creative about finding that angle measure. And I think that one good way to do this would be to use some alternate interior angles, to use actually the triangle sum theorem, saying that these angles all form 180 degrees. And you know, there are other options too. We could perhaps use a linear pair here to help us. But what I see is a pair of corresponding angles. Since I know that each midsegment, such as PH, is parallel to a side, which in this case would be side JL, then I can treat this side ML as a transversal. And that transversal is creating a lot of different types of angles, but the ones that I want to use are actually these corresponding angles that I've highlighted. When we have parallel lines, corresponding angles are congruent. So if this angle here, angle PHM, is 44 degrees, then its corresponding angle, angle JLH, is also 44 degrees. So now I can see that if I use this triangle, triangle JHL, then I know that all three of the angles inside that triangle are going to add up to 180 degrees. So we are just going to look at, let me find my other highlighter. We are just looking at this smaller triangle where we know, I'll highlight the whole thing. We know one angle measure is 76 degrees. We know another angle measure is 44 degrees. And we're trying to figure out what that X value would have to be in order for the three angles inside that triangle to add up to 180 degrees. So if I add 76 and 44, I get 120 plus X equals 180, which means X would have to be 60. So that missing angle there is 60 degrees. And to find that, we use two different things. We used corresponding angles, and then we also use the fact that in any triangle, all of the interior angles add up to 180 degrees. Okay, one more concept, and then we are done. Even though we might have some parallel lines that aren't necessarily intersecting shapes, such as triangles, we could have these parallel lines that are just being cut by a transversal. And remember, the definition of a transversal is simply a line that cuts through other lines in two distinct points. So in this picture right here, line AC is a transversal and line EG is a transversal. So we have two corollaries to talk about. The first one is called proportional parts of parallel lines. And that says that if one or more parallel lines intersect two transversals, then the parallel lines divide the transversals proportionally. So what's happening here is we have three parallel lines. It says that line AE is parallel to line BE is parallel to line CG. So all of these horizontal lines are parallel to each other, which means both of these transversals are being cut proportionally. I know this part AB compared to the part BC is proportional to the ratio of EF to FG. That reminds me of, to be honest with you, sorry to go crazy on the paper here, it reminds me of the divided sides theorem. That's exactly what it is, except instead of having your two lines come together and form a triangle, those lines just aren't connected, and it's represented as two lines that, sure, maybe if they continued, they could form a triangle, but right now we're just looking at part of that. And then the corollary that then follows that is congruent parts of parallel lines, which is that if three or more parallel lines are divided into three segments on one transversal, if three or more parallel lines are divided into congruent segments, that's an important word, congruent segments on one transversal, then they are divided into congruent segments on every transversal. So we're going to look at two different situations. Number 7 is going to go with the first corollary, and number 8 is going to go with the second corollary. So number 7, we have some parallel lines here, okay? So those parallel lines are cutting those two transversals proportionally. So that means, again, just like our picture up here on the corollary, it means that we have two parts over here on the left-hand side, and we have two parts over here on the right-hand side. So as long as I set up ratios with corresponding parts, then I can write a proportion. So I'm going to write mine like 7x minus 2 over 4x plus 3, 7x minus 2 over 4x plus 3 equals, and since I went top to bottom over here on the left, I'm going to go top to bottom over here on the right. So I'll finish that proportion with 9 over 8. If I cross multiply, I get 8 times the quantity 7x minus 2 equals 9 times the quantity 4x plus 3. Distribute, and we get 8 times 7x, which is 56x, minus 16 equals 9 times 4x, which is 36x, plus 27. Subtract 36 from both sides. I'm running out of room here, so I'm going to kind of skip a few steps for you, but if I do 56x minus 36x, I get 20x, and then if I add 16 over, 27 plus 16 gets me 43. And then if I divide both sides by 20, 43 divided by 20 gives me an x value of 2.15. So that's when you have transversals that are not cut into congruent parts. But on number 8, you've got some tick marks happening here. And if you think about it, if we tried to set up number 8 like we just did number 7, then I would be looking at something like 2x plus 1 over x plus 7 equals 3y minus 8 over y plus 5. And you would end up with a proportion that had two different variables in it. While you could set up a system of equations and solve it that way, I think there is an easier way. If we look at the congruent parts of parallel lines, if three or more parallel lines are divided into congruent segments, so see here, look, we have tick marks in congruent segments, then that means that the two parts that are cut on the opposite side are also congruent to each other. So we don't even have to set up a proportion on a problem like this. We can just say, to solve for x, 2x plus 1 equals x plus 7. And we can say for the y values, 3y minus 8 equals y plus 5. We don't even have to set up proportions to do those. So if we solve really quickly, x plus 1 equals 7, subtract 1, and it looks like we're looking at x equals 6. Do the same thing over here for y. 2y equals 13. So it looks like y is 6.5. And the way that we could plug those back in and check is if we plug those in and we got an equal ratio when comparing these two parts over here as the same as the ratio of these two parts over here. So that is all of our notes for today, and I hope that that was explained well enough that you can at least do your homework. Again, this section is not on your quiz that's on Friday. I'll go ahead and turn that back over just in case anybody was still, I rushed through those last examples, so just in case anybody was still writing down those last two examples. But what you're going to work on next, two things. You are going to work on a quiz review. So you're going to get a piece of paper that looks like this. You're going to work on the quiz review. I want you to work on that first so that I know for sure that you're going to get that done and I can handle any questions that you have. We'll take maybe 5-10 minutes at the beginning of the hour on Friday to answer any questions that you have over this quiz review. So make sure you get this done first so that you prepare yourself for your quiz. And then the second thing that you're going to get is actually your 7-4 worksheet, which is the homework from this lesson, and that's going to look like this. Honestly, I've taken less than 40 minutes of your time with this video, so you have plenty of time to finish both the review and the 7-4 worksheet. Again, I expect that you are respectful of one another and you are respectful of the substitute and that you are productive and work hard on what you have in hand right now, which is your math. But then if you find yourself done with all of your math, then you can absolutely work on other subjects as long as you do so without distracting other people. I know there will be a question about whether or not you can work with others. I would prefer that you didn't. You need to learn how to do this yourself, and when it comes to taking the quiz, you're going to have to be able to do that by yourself. So if maybe the last 5 minutes of class you want to get together with somebody and say, hey, did you get this answer for this one, or how did you do that one? That's fine, but for the most part, I would like you to do this by yourself. I hope you guys have a good day, and I will see you Friday, or some of you I'll see during seminar tomorrow.